Okay, guys, this is the third lecture of the waves unit, and today we're going to talk about electromagnetic waves, or light. All right, so what is light? It's a type of energy that travels as a wave, but it doesn't require a medium. So unlike sound waves that need at least air, most likely air, to travel through, or seismic waves that need like the earth or rock to travel through, light waves don't need a medium. All right, we call these electromagnetic waves. All right, because it's a wave that consists of electric and magnetic fields. It's sort of generated when you take an electron or an electrically charged particle, right? We'll kind of make it a little red one right here, and that particle extends an electric field out in all directions, like that, right? And when you move that charged particle up and down, you actually create a magnetic field. So this electrically charged particle can create a magnetic field, and it moves out in the form of a wave, like that. It propagates, we call it, out in the form of a wave. Now, similarly, when you move a magnet, you make an electric field. So it kind of goes vice versa. So there's actually two waves moving together. One's magnetic and one's electric. That's why it's called electromagnetic wave. These two waves move perpendicular to each other. Take a look at this. You can see here in purple is the magnetic field, and in red is the electric field. So when an electromagnetic wave moves from one point to another, these two waves move simultaneously together, but perpendicular to each other. So they kind of both create one another, right? So an electric field creates a magnetic field, and a magnetic field, changing magnetic field, creates an electric field. Think too when we've talked about how electricity is generated, right? The turbine turns, right? So what do you think the turbine is moving as it turns? It's actually moving a magnet, right? So the magnet is moving a magnetic field, which thus creates an electricity, essentially, that moves along the wire, okay? So when you're looking at this diagram here, you should really just get a sense that it's actually two type of waves together, right? The magnetic and the electric together, okay? So back to the idea that an electric field surrounds every charged object. So all things have a charge, either positive or negative, right? So if your floor has a negative charge, right, and your socks have a positive charge, and you kind of shuffle your feet along the floor, you can create that static electricity, right? You can see it there. You can see the positive and negative charge interacting, all right? So there's evidence that there's a field of electricity everywhere, all right? Also, all things are surrounded by a magnetic field. All magnets have a magnetic field around them, right? So if you can picture a magnet, right, here's like north, here's south, the two poles of the magnet. There is this field sort of surrounding a magnet like that, right, on either side of the magnet. All right, that's why certain metals that have magnetic qualities, like iron, steel, are attracted to magnets, because they're pulled toward this magnetic field. So when you move this magnetic field, you can generate an electric field, right? So that's why we use magnets when we generate electricity. So you produce an EM wave when you move or vibrate an electrically charged particle. So it's that particle again, right, that's sending out this electric field in all directions. When you move that particle, when you vibrate it up and down, you create an EM wave. All right, so that EM wave kind of moves from that. This vibration creates an electric and magnetic field together. They carry energy, all right, and they can carry quite a bit of energy. And remember, they can carry that energy through air, right, or space, or anything, or nothing, a vacuum, right? That they require no medium to move. So an electromagnetic wave, which I'm going to call an EM wave just because it's easier to say, less mumbling. That EM wave can travel through space from the sun, can travel across galaxies because it requires no medium. So we call this transfer of energy, right? So going from the sun to the earth, radiation. So whenever a wave is traveling from one place to another, that's radiation. All right, so the heat you feel from a campfire, that's electromagnetic waves moving from the fire to you, right? So If you are snuggling up with your dog in bed and you feel the heat from the dog, right? That's electromagnetic energy radiating from the dog to you. So when we talked about heat transfer in chapter 10, we were really talking about the transfer of electromagnetic waves. So they move fast. One thing you need to know that they move fast. We've all heard the speed of light. So far, we've figured out nothing moves faster than light. So in space, they can go 300,000 kilometers per second. That's not per hour. That's per second. So that's essentially how long it takes a wave of light from the sun to reach the Earth. It takes it not long at all. They'll slow down. It slows down a bit when it gets into other mediums, like air or glass or water. But through space, it travels really fast. So how can we calculate this? Well, just like any other calculation of speed, it's distance divided by time. Okay. So if you want to figure out how long it takes light to move, you just kind of rearrange the formula. So you can see it right here. Just kind of rearrange the equation. So time equals distance divided by speed. So we're just rearranging this equation here. So let's say we wanted to know how long it took light to travel 384,000 kilometers. Well, you plug in the distance. We know that the speed of light is 300,000 kilometers per hour. You divide the two, so it takes light from the moon, reflected from the moon, to get to Earth 1.28 seconds. So you can try this down here with that ridiculously big number to see that. So the distance from the sun to Venus is about 108 million kilometers. So calculate the distance. It takes the time it takes for light to travel from the sun to Venus. So go ahead and do that, and I'll check you on the next page. Okay, so if you did the math in the last one, it takes about 360 seconds or 6 minutes for light to get from the sun to Venus. So obviously it takes a little bit longer to get to Earth because we're one planet over from that. So let's talk now about light coming from the sun to us. So the sun is the major source of energy on Earth, right? We know that. We've done tons of talk about that. So we know that photosynthesis uses the sun, so it uses this EM energy. So it's crucial, right? And we know that because plants use the sun's energy, plants also make fossil fuels. Plants feed animals, which kind of all starts the food chain and whatnot. So it's really clear that EM energy is essential to life on Earth, on planet Earth. And the picture down below is just a sort of kind of brief summary of where light comes from, essentially. So it comes from the sun, but we know it comes from a fusion reaction within the sun where hydrogen is fused with other elements to form helium and other simple elements, right? So that fusion releases tons of energy in the form of these free neutrons and EM energy. So the light escapes that sun and reaches our planet and provides us with solar energy, with food for plants, with sweet suntans, and some other stuff. So we're going to talk in the next section about kind of what's within that light, right? So yeah, the light comes from the sun, but it's not just light, right? The electromagnetic energy has actually a lot of different properties, a lot of different uses, and is pretty, there's a whole spectrum of things, right? So we're going to talk about that in the next section. So again, just kind of back to the importance of EM energy. Fossil fuels really get their light from the sun. Their energy from the sun. Since they were really just plants and animals that have died millions of years ago and kind of died there. Okay. One last thing is that we're not really getting all the energy from the sun that the sun puts out, right? A lot of energy trails away to space, goes in different directions, reflects off the Earth, and we only get imagine taking like a light bulb, right, and then holding up like a bowling ball to the light bulb. A lot of that light that leaves the light bulb goes in all directions, right? It doesn't all focus on the bowling ball. Only a sliver of that does actually lights up one side of the light bulb. So there's a lot of energy coming from the sun, and we only get a fraction of it. So Yeah. So on your quiz, guys, just make sure you know about what kind of waves EM energy waves are made of. Know that they don't go through any medium, right? They can travel through a vacuum. You should know the speed of light, and yeah, that's about it. It's a very short lecture today. Study up for your quiz, and I will see you on the last lecture for this chapter. Thanks.